So let's get started for sure. Now, we've really reached the end of the, what we're doing here is that paper. We've reached the end of it, the logical end. There is a conclusion section and some other things. And I really didn't want it to end because there was a couple of topics that I feel could have gone in the paper. I ended up not doing it because of space concerns, and I just wanted to get it out. But I do want to do them here. And the first one I want to do is the frequency domain. So we ended up, where did we end up? We ended up doing what the chapter that I called economic engineering. So this is, all this is theory, okay? And here we became real engineers and we're building first order systems and we're building these second order systems. This is a broker-dealer, you know, with this, he's trading, he's got his storage, he's got transaction costs he's making. And we look at his response and we try to understand it in terms of discounting, hyperbolic discounting, blah, blah, blah. All these formulas that you know so well, we've done here. We've done the same with an alternative system and showed how it relates to future markets. And this was all just kind of practice in taking a time domain problem, which is the Newtonian approach is in the time domain, and then trying to understand how this very simple systems like this can be interpreted purely economically or financially. Now, if you look at these type of solutions, and if you're a control engineer, you wouldn't solve this in the time domain. You would immediately jump to the frequency domain. I mean, so how can we take the frequency domain with which we're so familiar, where we love to be in, and interpret that in terms of economics? Okay, that's what this lecture is going to be about. And to me, this is a beautiful theory. I mean, it's kind of stunning, and I want to share that with you guys. All right. So here I kind of dive myself into it, but let me just start at my second slide. Now, you're not supposed to understand any of this yet. I'm going to get there. But this thing you'll recognize, like this is the Laplace transform, right? There's just some function v. This is the velocity. So here, that's some flow. This could be some flow of money, right? And it will be a cash flow, right? Huh? And then I'm just taking the Laplace transform of this thing, and I'm getting something else, okay? Which is the Laplace transform of this cash flow. I'm just assuming these commodities are as money now. All right? Huh? So normally, if you have a Laplace transform, you kind of remember this, and then they teach you a little bit what it is and how you would have to calculate a Laplace transform, and they tell you very quickly to forget about that, and they give you a table, and you just look them up, right? And we all know this table, right? Boo, 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 this one, up that table, the step response is whatever else, and la, 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 right? Huh? But why? Why would you do that? Well, if you look at this, you know, this you would call, if you're an electrical engineer, you would call that the current, and this you would call the frequency domain current, actually, right? And this will be the frequency domain voltage, and this will be the voltage. Let me ask you this. If this is a current, what are the units of this? And a current is, what's amperes? What are the units of this, the Laplace transform of a current? Does anybody know? Charge, yeah. Is that what you would expect? You would, yeah. Would you have expected that? Huh? No, but what's the, you know, a current. You know what a current is. That's so much charge per second, right? Huh? So many amperes. Now you take the Laplace transform of a current. What's the units of that? Is that also amperes? That's my question. Is that the case? Huh? Yeah, you won't get amperes, right? So that's very good. You get charge. No, because you integrate over time. If this is charge per second, and this is d seconds, then these will cancel, and this will be charge. All right? Okay? So the Laplace transform of a variable does not have the same units as the variable itself. That's obvious, okay? All right, huh? So he was right. But there's not something, if you call this the frequency domain current, that's not something you would expect. You would think of this as a current, and it really isn't. It's some amount of charge, right? Now, if this is a force, then what are the units of the Laplace transform of a force? Okay. Is that Newton? No. What is it? Yeah, it's Newton time. And what other object in mechanics has units of Newton times time? Impulse, yeah, momentum, right? Sure. Momentum is the integral of a force. So there must be a time integral of a force, okay? But it's not momentum. It's like a momentum, okay? So this is kind of a sort of a slip that we use. We think of this as the frequency domain force and the frequency for this, but really it's a different object. It even has different units, right? Because what is this thing doing? It's taking a current and it's weighing it with some factor and then adding them all up over time. So this is a total amount of current in the future. It's going in the future. So it's looking in the future, adding it all up, right? Huh? Weighed by some factor and boom. All right, huh? Okay. Right. Now that's a little bit what's wrong with the lookup table approach. Like you never really ask yourself any questions anymore. You start just looking things up. All right. Huh? But you will see if you look at the lookup table that these units are indeed, you know, whatever the units of this were times time. Okay. Now let's become economic engineers. And what if this is a cash flow, right? So many dollars per year or something. Or some commodity, so many items per year, I don't care, right? What are the units of this thing then? Well, dollars or items, right? Huh? Okay, obviously. Now, why is that obvious? This is a formula. So you take, so this is a cash flow. So suppose this is a cash flow. Huh? So you take a cash flow, and at time 0, you get a payment, say $1, right? Okay? And then you multiply that by some factor. Now, in this case, the factor is 1, because e to the minus s 0 times 0 is 1, right? Huh? Okay. And a little dt just says, okay, I got, huh? Here's my cash flow. I'm taking this, huh? Boom, huh? And then I take the next one, and then I hit it down a little bit, right? But I add it up, right? And I add it up, and I go from 0 all the way to infinity. So what I'm doing is I'm looking in the future, I'm weighing that future with a factor, and then adding them all up, all right? Now, if you think of this S here as the interest rate or the discount rate, okay? Then what this thing is doing, it's taking an amount of money you receive at some time t, discounting it with this thing called the discount factor, okay? All right? Well, this is the amount of money, there's Vt dt, and then doing that for all future times, adding them up, and you get this quantity of money here, right? And you know what that is called? That's called the present value, all right? So the Laplace transform of a cash flow is called the present value. Why is it called the present value? Because you take all these values and you bring them to the present by discounting them. But this is the discount factor, okay? All right? This you should have learned at school, by the way. All right? So what you should see here, that's this formula, which anybody knows who's done any type of banking, right, is the Laplace transform. All right? There's a piece of insight right there. And then, of course, the present value doesn't have units of cash flow because you took the whole cash flow and you said it's worth so much. All right? So it's totally obvious they don't have the same units. Okay? Well, secondly, this whole formula that used to be something that's mysterious that you got to go and, you got to go and, I'll think what it was, is this completely trivial, right? Okay? Now, there's one thing that's not so trivial, and that's what we work out, is that normally if you do banking or finance, this is a real number, okay? But we use a complex number. This S is sigma plus I omega. Okay? And this I omega, that's the killer. All right? This is nobody in finance has this. All right? That's the cyclicity that's in the signal. This is the discounting that's in the signal. So this Laplace transform does a little bit more than just calculate the present value. It also takes care of how cyclical the signals are. That's the Fourier part of the Laplace transform. And this is what makes this thing really work. One of the things. The other thing that makes it really work, and we'll get to that, is that we, rather than a nice number that you throw at somebody, right, we use these as signals. So we see it as a function of this discount rate. And then this can be processed and it becomes another function. All right. Okay. So all hell is going to break loose now from this simple insight. Okay. The other thing you got to realize is we're not just looking at a bunch of cash flows. This could be any type of commodity. And I'm looking at the present quantity, whatever that is. There's some amount that's equivalent to receiving all these bushels of hay or corn or whatever it is at the present if I discount them. Okay? And now look at this guy. This is a desire or a want. But I have all these future desires. I can want this then, or I'm going to want this then. What if I bring those all to the present, right? Then I get one big kind of willingness that I have to, in the future, do all this stuff, all right? That's this Laplace transform, okay? Sort of a price, whereas this one was the derivative of a price, okay? So our two conjugate variables also have their own Laplace transform. We can work with impedances. We can work with reactances. We can do all the things that control theories love and do so well. But with one big exception, we have a great interpretation for what this all means, instead of staring at this as some formula. All right? But don't forget, you can still use a lookup table, right? So does anybody remember what the Laplace transform is of a unit step? Yeah, 1 over S. That's right. Okay. Now look at this thing. Suppose this is a step, huh? This is a cash flow. What does that mean? That means you get an amount of cash. This is very typical, like a salary, right? Turn it on, and boom, you just get this payment, right? Huh? Every month. Boom, 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 boom. Huh? Okay. What's the present value of that thing? That's what you call a bond or a console or a perpetuity. There's just a bond that pays interest forever. What's the present value of that thing? Does anybody know? Accountants, they know this. You know what I'm asking? So you have a cash flow, right? You get €1 a day or something for forever. What's the present value of that thing? What? No, of course not. Why would that be infinite? Okay, all right. No. You do 1 times e to the minus st dt. Okay? Huh? No, is that 1? I wouldn't say so. Huh? Oh, come on, guys. You just said it. It's 1 over s, but whatever, right? Huh? Okay. So why can't you now say it's 1 or infinity? What is the integral of e to the minus st? Well, between 0 and infinity, one of them because it's going to be 1 over s. All right? Huh? Okay. Sure, you integrate this function, you get 1 over minus 1 over s, e to the minus st. All right? Huh? Okay, guys. Huh? All right? Huh? But you already knew it. You already told me the answer is 1 over s. Okay? So it's infinity when the discount rate is 0. Sure, when the discount rate is 0, it will be infinity. When the discount rate is infinite, boom, you don't care about anything in the future, and this thing will be 0, right? Huh? Okay, clear. All right? Okay. And otherwise, if the interest rate is a half, this is worth 2. So a cash flow to infinity is worth 2 euros. if the interest rate is a half. Because you discount, all the stuff in the future is worth way less, and it just converges. Why does it converge? Because this is a convergent function, man. Huh? All right. Okay. What's the Laplace transform of the unit impulse? Yeah, 1. So what is a unit impulse economically, if you look at cash flows? No, it's just a payment now, right? There's one euro right now, here, boink, huh? In your lap, right? 0 seconds. How much is that worth? Okay. At your leisure, you can go down that old table, huh? If I had more time in this lecture, I would do that. I would go through that, and we'll do this. But you know, huh? All right, huh? See, huh? You can take your table and just sort it out, huh? And it just makes sense. All right, huh? Think of another one. You have A minus S, right? That's like the DCF model, dividend discount model or something. You know, you get dividends at A, and then you discount it, and huh? Something like that. I won't talk about this. Okay. All right. For some reason, everybody turns into Mickey Mouse when it, you know, when you do this exam and you know your table is all fine, and as soon as you have to think about it, what it really means, then you just say infinity or something, right? Huh? Okay. Huh? Don't do that. Huh? There's immediate connection. It's very beautiful, actually. It's very beautiful. Okay, because this is one of the things I love about economic engineering. All these things that are so abstract, this become immediately clear and obvious and why it should be that way. All right? Momentum is so abstract, but a price is not. Energy is also abstract, but surplus, a profit, is not. Okay? And present value is not abstract, but a Laplace transform, you know, huh? Laplace transform is like somebody of the opposite sex, you know, like you never really understand it, but you kind of get used to it after a while, and you know what you can do with it, and you know, and it's useful, and you know, huh? So, huh? No lookup tables now for solutions. Yeah, it's like a Laplace transform without the lookup table. Huh? Yeah. All right. So this is where we want to go. Okay, this is cool stuff. You know, this is stuff we want to know. And now, and as long as you talk about S, you know, as a real number, everything is really clear economically. The trouble starts with what happens to imaginary, you know, complex discount rates. And that's where most of this discussion will be about. And then the other thing it will be about is about how we can use it to solve these linear differential equations, you know. So what's the economic meaning of that? You know, what does multiplying by S mean, you know? Huh? You know, if you have a differential equation, every derivative is a multiplication by S. What does that mean economically, right? That's the questions I really want to answer, all right? So let's first talk about imaginary numbers. So they are one of the things about what I don't like about imaginary, the name, is that they're called imaginary, and they're not imaginary at all. All right? Huh? So the way you should think about imaginary number is it's something totally real in the sense that it exists. Okay? And I just want to do my little spiel here. All right? First, a mathematical spiel, what it is, and then how this applies to economics. Okay? So there are really two stories about the origin of the number I. One is, which is told by everyone, is that, okay, it's a number such that this is the case. This is what you don't want to do. It's true, but this is not how you want to think of it, okay? What you want to think of it is more geometrically, all right? And I'm going to use this thing here, all right, to explain this, and then I'll show you how you can give it economic meaning. So This actually goes back to how numbers were invented. So the ancient Greeks, they had these numbers, right? They didn't have 0, but they had 1, 2, 3. And then they could divide them. They could get a half and stuff like that, right? So they had all these positive numbers. And it just comes from counting. Here's 1 laptop. Here's 2 laptops, you know. And then you can saw it in half. I don't know if you still have a laptop, but some stuff you can cut in half, you know, and then you can come up with a half, right? But what's a negative laptop? That's ridiculous, okay? Huh? Right? Even 0 laptops, you're just wasting your time counting something that doesn't exist, okay? But then you make a step further and you start doing, what is it called? When you measure land, huh? Geography and stuff like that, right? So there's a famous mathematician called Gauss. Huh? That's what he was. He was in the employ of Brandenburg by the prince or the elector or whatever his name was. And this guy was interested in how much land he has. So Gauss had to calculate all this stuff for him. So he was a geometer, Gauss. Okay, and Gauss, he had this different interpretation of complex numbers and how everything goes. So he started looking at numbers as something where you measure things with. Now, in measuring, what you do is you also count. So, you know, measuring rod, you say, okay, 1, and then I do 2, and then you have 2.5, so you break it in 2, or you go, okay, it's 2.5, you know. Huh? So that all works, so you're just still counting. But the thing that's nice about measuring is that if you stand here and you start measuring to the right, you have positive numbers. But what if you start measuring to the left, okay? Say, well, it's not the same, right? Or in a different direction. So you really want to have some numbers to represent that, okay? So what you do is you invent these negative numbers, and what you're really saying is, I'm just going in the other direction. That's all I'm doing, right? Huh? So if I'm standing in a plane, you know, you don't need to be standing in a plane. You can just say the other direction. But if I were standing in a plane, it will be a 180-degree turn, right? Huh? Just a right turn. So if you are somewhere and you say, oh, damn, I wanted to go to the other side, what you would do is you want to turn this 180 degrees. And how do you do that algebraically? You multiply by -1. So if this is x, you multiply by -1, and you get minus x here, right? So the act of multiplying by -1 is equivalent to rotating over 180 degrees, okay? That's what you got to see. If you rotate another times over 180 degrees, so that's 360. You multiply another time by -1, you get -1 times -1, which is 1, and sure enough, you're back to where you started, okay? So it works. It's a consistent. So multiplication becomes an operation, right? And it's an operation of rotation, all right? Okay? All right? So negative numbers give you a rotation of 180. All right, now if you live on a line, that may be all you've got, all right? And maybe these laptops live on a line. But Gauss was in the plane because you have to measure the land. So he said to himself, and I'm just making an apocryphal story, all right? It's not that he really said it. He says, okay, I also need to rotate with 90 degrees, okay? And that's another 1, right? I'm not going to put a minus sign in front of it. I already did this. So you know what? I'll use the Roman letter for a 1, an I. The Romans use an I. I use a small 1. All right? So not imaginary, Roman 1. Okay? Okay? And then I can go the other direction. I'll have the Roman -1, right? That's still 180 degrees. Okay? Now that's fine and well, but that only works if you do a 90-degree rotation. You take 1 and you multiply it by I, right? And then you're here. That worked. Now I want to rotate another 90 degrees, so I'll multiply by I again, but I have to get it -1 because that's what I defined, okay? All right? So basically you see that I squared is -1. That's the only way to do it, right? So all this is saying is that if you rotate twice over 90 degrees, you're going to get 180 degrees, and all this is saying is if you rotate, you know, now twice over 180, you get to 1. All right, okay? That's what you got to see here. Now you can rotate over 45, you know everything, because you take a square root of I, and then that's 45 degrees, etc. And you can work that out with e to the I t. You'll sort it out, okay? All right. So So no, nothing imaginary about it. There's not, I mean, it's only imaginary if you are a being who lived on the line. You can't imagine what that second dimension is. So fourth dimension for us will be an imaginary number, sure. But not this. This is not, okay? So that's what I don't like about that. And secondly, this is just easy to remember, all right? Okay? So this brings us to the meaning of that I in the Laplace transform. It's got to be something like that. You've got to be rotating about 90 degrees, okay? Right? So when does that happen? All right? So it's actually one of the most natural things that you can do. So up to now, we've just been considered goods like they were just flowing. All right, here is some oil as it comes out, and here's some grain, you know, as if it's a laminar flow coming from somewhere. But that's just not the way it works in practice. So these grains or apples, or this is grain, I think, or wheat, I don't know what the guy's got. What happens is they come in cycles, right? So only when you harvest, where's the harvest is here, right? Do you get real grain? Now this one kind of sucks because this is the real dimension, right? But that's okay, you can deal with that, right? You guys are abstract, huh? And then suppose this is your grain silo and this is your, you know, zero level, you can go below it or up, right? So what happens is when the time goes on, then you first go, and then you need to plant here. So you first your grain goes down, and then you start planting, and you start using more of these seeds, and then it comes out, and then and then that's how you turn around, right? Huh? So you see that the cycles of the year, what they do is they give you a natural cycle of seed harvest and seeds, you know, and product and yields. Okay. Huh? So here will be the real axis. So this will be +1. This is sort of an imaginary thing, right? Because you're just protecting your future things. Okay. Here you have -1. Your reserves are really low because you're planning it, right? Here's another imaginary one, -I. I just did it this way. You know, you can do anything you like. You call this -I for all I care, right? Huh? Okay. This is the prepare part. So I'm preparing. That's maybe in the imaginary direction, 90 degrees, and then here, huh? Okay, and there are 360 days, give or take. All right, so every one of these is a degree, you know, and these are the 3/4. This is how we do our semester. This is a semester, is 180 degrees, all right? Huh? And you got the basic rhythm of farming life right here, okay? And in a sense, this is where economics started, is when human beings started farming. So they had to work with the cycle, the yearly cycle, okay? So here is your imaginary number, all right? So this grain or this harvest is not coming in a flow. No, it's coming in a cycle, and it's not like you can throw away the imaginary part. The farmer can't do it. He has to protect, he has to prepare, he's got to do all this stuff. It's all real to him, all right? He's just, this is, I don't know when this is. This is, I think, the fall somewhere. This is like whatever. These are all these different seasons. He's always busy, all right, doing stuff, okay? Just like if you want to go from here to there, you got to go through there if you're in the plane, right? Huh? Okay? All right? So, very natural. Our whole way of counting days, the whole way of thinking, this is, an economist will call a signal like that seasonal because of it, right? Huh? Now, we have a tendency when we have the complex solutions to throw away the imaginary part and saying it's irrelevant, you can't see it. This is not right, okay? This is the meaning, all right? There's something happening in between that we're not seeing or we're not registering or we're not looking at, I don't care, right? Huh? But it is real, all right? Huh? Okay? So as soon as you start looking at these kind of things that go in cycles, that's when you start using a Laplace transform that has an imaginary part, not just a real part. No, you're not just discounting, okay? Like you do with money that doesn't really have a season, all right? There are very few cycles, but they do, by the way. You have the credit cycle, okay? I think this is part of a credit cycle. It also goes in cycles. You know why money goes in cycles? Well, precisely because this goes in cycles. This money was invented to facilitate this, because when the farmer has to plant, he has no money. Okay? When he has to protect and prepare, he has no money. He makes all his money at harvest, and then he needs credit, and he will pay it off when he makes his thing. All right? Now, before, these farmers would have some savings and tucked away, but nobody could get into farming because you needed some, and you had to borrow. And then there were, in the Middle Ages, you had a big Jewish population that would then loan money and borrow and do this. But there were no banks to provide this. But this is why it was invented. Huh? Because of the cycle here, the money also has to go with a cycle. Okay? So the credit cycle is at the same rate as the, all right? Huh? Now, there are other cycles that are a little quicker, but this is the Ur cycle. This is where it all began, right? Huh? Okay? Especially in the northern hemisphere, where we have, or southern hemisphere, we have 4 different ones. I think if you go on the equator, you only have a wet season and a dry season, and maybe only 2 cycles. But we are thinking in quarters. And okay. Bonds are traded on cycles, so every half year you get a interest rate payment, right? Sometimes they're quarterly. Huh? Accounting is done on cycles, quarterly accounting, half year, year. All right. Bond market is open, I think, 360 days in a year. Hardly a coincidence that there are 360 degrees in a circle, right? Huh? It's just the way. So I somehow feel that all this stuff, which we're now saying, okay, this is hardcore engineering and science, but maybe the fit with economics is where it all came from to begin with, right? Because this is the way we've internalized our thinking. All right? Okay? So now you can think of this S parameter, this S plane, as consisting of a discount rate. So we still have our regular discounting, but we can also put in an omega that tells you how fast you're going through your cycles, okay? And this will be then a yearly cycle, but you have things that go faster, okay? We'll see them, all right? And I drew this little figure here to show you a little bit of a more general thing than farming. So you realize P&L, and then you have unrealized. This is how an accountant will look at it, right? Huh? So you can make that distinction. You can make a distinction between cash money and credit money, and then you first borrow, and then, all right? Huh? So you just recognize the cycle in many, many places. Now, if we go back to our solution here, remember we had this complicated discount factor here. It consisted of a real part and then this oscillatory part here, okay? This is also a sort of oscillatory part, but it's kind of a limit case. And this is a hyperbolic oscillatory part, okay? But just focus on this one for now. So this thing can be, this is all real numbers. We can just treat this as a complex number, right? And then this oscillation is way more natural because this is just a cycle that the trader is going through, right? So every trader goes through a cycle. You buy, and then so much. If your currency exchange, you buy all your currency, and then you go with your desk, and then you sell it, and you low, and then you buy again, and you sell. And nobody is just passing it through, right? Huh? Everybody has a store, and he is maintaining a price. So they all have a capacitor, and then they have an inductor, right? Huh? So they're all going to maintain a frequency at some kind of rate, okay? So it's better done with complex numbers. So you see here the cycle, and we can make now, what we'll do is, instead of that complicated thing, we'll just make this little discount factor, okay? So for all that analysis, all of a sudden, we'll just do a switcheroo and make this, so here's the discounting, and here's the cycle. So if I'm here, you can see the discounting part, and then you can count the cycle at which this trader is operating. All right? So, just to summarize, we can define a complex discount rate or a complex frequency. You see, we start with the frequency part, and then we add the real part. It's called analytic continuation. So the Fourier transform was there first. The Laplace transform was kind of only for real numbers. And then they put them together, and they have the complex Laplace transform, and then they added this part, right, to look at damping. Now, the damping, as you know, that's a trade friction. That gives you the regular discounting, okay? Huh? So we would say it's the complex frequency rather than the pure, real frequency, this thing here, right? Economists, they probably would start here and only recognize that they have some discount rate. And the frequency they do, but they fit it. It's a separate thing. So they don't look at the business cycle as part of discounting process. With this approach, we can configurate them. Huh? We can put them together. Huh? And we get one kind of complex discount rate where the business cycle and trade cycle is sitting here. Your discounting rate is sitting there. All right? It's very, very, very efficient. So I have to keep this apart. All right? And then that's the discount rate. And the thing that goes in the Laplace transform, that's that discount factor that we've been arduously calculating in the time domain. Just plop it down, right? Okay. And the meanings are all in this whole picture here. All right? Clear? All right. So let's go and then do something with it. So now I'm going to go back with that insight and now work this out. So I know now what this thing is and where it came from. All right? And now I want to define this thing called the Laplace transform. Now, there's a couple of things that are easy to misunderstand, but are important to realize at this junction to understand what the difference is of our use of the Laplace transform in the frequency domain and the use of just the present value. All right? So a present value, as used by economists and financial and accountant types, is just a number, okay? So you have some cash flow, and you attach to it this number, which is the present value, all right? The Laplace transform is a function, all right? Okay? It's not a number. It has tons of numbers. One number for every value of this complex discount rate, S, okay? This is a very, very important distinction. So the way an economist looks at a signal, he looks at it, he calls it a time series, he won't call it a signal, and then he will calculate something about the signal. Boom, here it is, right? This is the mean square fit or something. What we do, we leave the signal intact and we manipulate the entire signal in one go, not just some number that summarizes the signal, okay? So we'll take that signal and push it in some box and see what signal comes out, okay? All right? Then we'll transform the whole signal, push it in a box, and see what in the transform domain comes out, okay? So the way you can view a transform then is that it takes a function in one domain and maps into a function in another domain. So it's kind of sounds, you do it all the time, but you don't really realize you're doing it, right? So you can think of some big space. It's a huge space, of course, of all time functions. And here's one, right? Here's another one. It's way bigger than a plane, of course, because a plane you can have only a function with two values. And these are continuous functions, right? So sometimes there's names for these. It's called Hilbert space or Banach space, but that's immaterial here, all right? Huh? I guess for a Laplace transform, you'll need a Hilbert space because it needs to be square integrable. Yeah, because you're squaring something here, right? But, huh? So, but that doesn't really matter. And then you map that whole thing into another kind of function domain where you get these Laplace transforms, okay? Huh? So don't just see this as an entire mapping. So it's almost like this is a vector, and here's another vector, and then this Laplace transform is some sort of big matrix multiplying this vector times this matrix to get that, okay? You see, this is like a matrix. It has two variables, rows and columns. This is like a vector. It only has a, this is the other vector, okay? This is called an integral transform, okay? This should be trivial, or all known. Not known explicitly, but just, I just see a lot of students when they start using the Laplace transform that they think it's a present value, and then they stop using it as a function, all right? Frequency domain function. So it's nice to make that comparison, but you got to see that you're going way, way further, all right? Otherwise, you can't do controls with it. If you just have a number, what are you going to do with a number, right? How are you going to get a Bode plot, all right? All right. So that's what it is. Now you can take the Laplace transform of just about anything, but the two most important things are the velocity and the force, okay? Or a current and a voltage, or in our case, the flow of goods, or the quantity demanded, and the wants and desires or incentives, all right? And these will be giving special names, just because they're so essential. And you can get everything else from all other variables from these by just multiplying or dividing by s anyway, right? Okay. If you're an electrical engineer, this is basically all they look at. We may look at momentum and other things, but they don't even bother, all right? Now, this one we already talked about. So if this is a cash flow, right? So if the commodity is his money, then this is the present value, right? But if this is just some sort of demand or some oil, then it's I would say present quantity or something, right? So it's a present quantity demanded. It's some sort of demand. So this is the quantity demanded. So you would draw it on some demand graph, right? You could do it here, right? Instead of that V, right? But it's a little bit cheating because this is like a complex number. So you're drawing so this thing is going to be a complex number. So you you have to see a plane here, okay? And the units are different, right? So these are just a quantity. This is also how economists often think. They don't really see the quantity demanded as a flow, right? They always see it as a bit like this that has no time associated with it. The mistake they make, it also doesn't have a discount rate associated with it. So whatever, right? Then it does nothing, then, okay? So I guess what I'm saying here is, as engineers, we often make no distinction between these two. Like electrical engineer may use a small I here, a big one, they don't even care, right? And you can do kind of the same here, okay? Just, you could call that a quantity. Just remember that it's not a flow in time. It's just something on the spot market now, all right? Now, you can do the same with your wants, all right? So I want this at time 0, I want something else, and I have to add these all up, right? So I'm talking about my desires and in the future, right? Now, what's that? What's a desire in the future? So I'm saying I don't want it now, but in 3 years' time, I would want this, and but that's less important to me by this factor, now, for my total whatever I have now in terms of desires, right? So I would say this is your willingness, okay? It's not your desire, but it's your willingness. It's your willingness. Willingness is about the future. Your will is about the future, what you want in the future. It's not about the past, right? Desires are about and willingness is also not about the now. If you say, I'm willing to do that, you mean about a future date, you will do that. If you're willing to do it and you're doing it now, obviously you're willing to do it, right? That's when you would use a desire. A want is something immediate that's happening now. So this is the want, and this thing is your willingness, okay? All right? So it's the Laplace transform of an economic force is your willingness. And you will see, so there's another complex number here. I'll call it P for price, because it has the units of price, right? Now, when economists draw this kind of graph, they will also call the price the willingness to buy, right? And that's why I call it a willingness to acquire. To buy means that you're exchanging it for money. We don't want to take that interpretation. This is just a value that I assign, all right? So I call it a willingness to acquire, and it's some sort of price, but it's a frequency domain price, okay? Okay. So I like to make a distinction between your want, then your real price, which is your time domain price, is just momentum, and then this willingness, which is the frequency domain thing, okay? I even think of this thing without the integral as an intention, right? So I have an intention at 10 years from now to do that, right? Huh? And all my intentions added up, all right, is my total willingness for the future, all right? Huh? What I'm doing here is just finding words that we use in everyday language and seeing if I can identify concepts to make it. Often the right word is like 90% of the job, because it puts your intuition the right way, and otherwise you're sitting struggling with a term like entropy. Like you can never really get your intuition working for that, okay? And a great thing about economics is everybody does it. So it's like Eskimos have 24 different words for snow, and we have all these different words for different types of forces and stuff, okay? And it's important to leverage that. Okay? So now I have the Laplace transform of the quantity demanded. So the velocity of this, of the economic force, that's my willingness. And now I can do stuff like, look what happens when I have a system like this, okay? Now, this is what you would call the elasticity. Okay. This thing, H of S, why is this Y? This should have been H, okay? So the transfer function, now, this is the way you do it. Suppose you have here's a system, you know, so it's like the systems we had here. You know, these kind of systems. Boom, you put a force in and you have this kind of system, and it's this differential equation. So I'm taking a system like that, okay? I'm just bringing it into the Laplace domain, and you can do it like that. So you take this velocity here in, and the force is coming out, right? And then what is the transfer function? Well, in an obvious way, it is, of course, I think I did this wrong, right? It's P over Q, right? Huh? Yeah, because I use Y here because I wanted to use the admittance rather than the impedance. And this is this the admittance? What is the impedance? So the impedance is what? That's the impedance. How do you say the impedance? I forget. Is that an R or something? Huh? That is, so V is I times R. So this is V divided by I. So that will be the voltage. So Vp divided by Q. That's the resistance. Yeah, that's the impedance. Okay? That's the impedance, right? Huh? You know, if you have electrical impedance, you know, you push some current in, and then you look at what velocity comes out, right? Huh? But it's a higher order system. It's not just a resistor. So instead of resistance, you use this word impedance, okay? So this is right. So P over Q, that's the impedance. So that's the inelasticity, as it were, a frequency domain inelasticity, right? It tells you how hard it is to get your goods through, right? And so what I wanted to here is the admittance is how easy it is. It's the inverse of the impedance. Oh, the impedance is a Z, right? I think it use Z of it. Okay. That's what I intended to do here. So this should have been a Y, because Y is the symbol for, is that right?
Yeah, C is V over Y.
Yeah.
I think in the next slide you have it.
Yeah, but correct, probably, yeah. Anyway, this is just a didactic slide. You know, I put in errors so that you guys. So, okay, what is the point I really want to make? If you have these Laplace transforms, so you have these present quantities and this willingness, you can define things like impedance and admittance and in general any transfer function. Okay? Now, how would you call those? Now, economists have only one word for all of this, and that is elasticity. All right? So this would be the price elasticity of demand or something. Okay? This is what they would say in the frequency domain. We have an elasticity also in the time domain. All right? But we'll just use the same word. Okay? And then the inelasticity would be the impedance, and there's tons of others, okay, or possible combinations. So if I would plot that on the economist graph, and here I would have the demand, and here I would have this willingness, this price, frequency domain price. And then here will be some linear relationship, right? Now, if you have two real numbers, then the slope is a linear relationship, right? So slope is a member of RP1, right? So it's projective space. So all slopes are on a circle, right? All possible slopes. I think half a circle actually. Okay. But if these are two complex numbers, then you need a complex circle in order to get them all. So that's called complex projective space, and that's what all these ratios are, right? So they're kind of complex slopes. You follow that? If you have a ratio of two numbers, it's always a slope, right? Because you have y over x. But these are complex numbers, so it can't be a real slope. It has to be something else. It's called a complex slope. It's actually, and slopes, so complex slope, I think, is there's names for it. They are, what is it? The Mobius transforms and all kinds of stuff. It's not so important, okay? What you got to realize, some students think that this is also a Laplace transform of something. It isn't. It's the ratio of two Laplace transforms. Okay? It's not a Laplace transform. Only for very special cases when you have an impulse and you know, because what are you doing? You're really dividing by one. So of course then it's impulse response, you put one here, right? And of course then it's a Laplace transform. So a ratio is not the same, of two numbers is not the same as a number. All right? Okay? Very different properties. It's not so apparent. It's a little bit apparent I mean, if you have a ratio of numbers, that's the slopes, right? So here's a slope, here's a slope. But what's the space of slope? Is that a line? No, it's actually a circle, right? Here, every point on a circle is a possible slope. In fact, it's half a circle because these 2 points are the same. So the topology is a weird one, right? There's a name for that space. It's called real projective space on one dimension. All right. Now, if you have complex numbers, it gets a little bit more complicated. But this is just a warning. All right. So this ratio is a complicated object, and that's what we call the transfer function, and that's an elasticity. Compared to what economists do, the difference is that these should be functions of S here, and the relationship is one between two complex numbers rather than two real numbers. All right, so way more complex, literally and figuratively, way more complex. But the language we'll use. But just remember that these, in the frequency domain, they are complex numbers, okay? All right? Now, you can stuff anything in here and see what, and get anything out as here, right? So you don't really need only admittance, you can have some generalized transfer function. And that just tells you how one signal, signal input relates to an output. All right. Now, why go through all that? Well, we all know why, right? So suppose you have another one here, you can just multiply them rather than convolving. It just gets easy. So you have an algebra of systems, and but that's for another lecture, how we can use that to build bigger systems. Okay? Here I just want to make the connection. But you can do both. You can just do the other thing or work with the time domain. Okay? You all know this. Now, okay, once you see this, you can write, and there are certain conditions, we won't worry about it. Any of these transfer functions can be written as a ratio of polynomials, right? So we'll just take polynomial transfer functions. So this is the order here is the mth order and the nth order. These are the poles, the ones where this is 0, this is what we call the zeros, right? And here's some overall gain of the transfer function, okay? Now, look at that for a second. What's happening here? This S was just a complex frequency that I was saying what the discount rate was and how you were turning. But now, what are we doing? We're multiplying by S, right? And you're taking some signal time, Q of S, and you're multiplying that by this whole thing, so you'll get S times Q of S somewhere, right? Times B. You see that? Huh? You follow this, what I'm saying? I went a little fast. If you have a transfer function like this, then you know this is H of S times Q of S, right? This P. Now, if this H of S has got all these, a factor of S in there, what you're going to end up doing is multiplying your Q, right, that quantity, by S. What's the meaning of that, right? We knew that if we had an e to the minus st, what the meaning was there, right? That was just, the envelope, the modulation and the frequency. But now I'm multiplying my S, okay? Now, why am I doing that? I'm doing that because that was from an engineer's perspective, that's the whole trick of this, is that I don't want to solve a differential equation. I want to solve an algebraic equation, and I don't have any derivatives. I'm just looking at squares, and I'm solving, the characteristic equation, determinant, blah, blah, blah. I'm feeling good. But what am I doing here, right? That I wanted to give some economic meaning, okay? So let's do that, all right? So suppose, this is really how the Dutch taxman works. So suppose in Holland we have this thing, and you probably know this, it's called forfaitaire rendement. So if you have a house, right, the government wants to tax you on this. But how are they going to do this? They can't really say, I want a piece of that house, okay? So what they do is they say, all right, suppose that house is worth so much, the present value of this house. We make an assessment, the Volkswaarde, right? So many euros, okay? Here, boom. Then they say, well, because you're living in it, you're receiving all these benefits of shelter and comfort and all of that, right? How much are you receiving? Well, we're going to multiply this by some rate, right? Okay, say 1% per year, right? Okay. And this we will call a forfaitaire rendement, all right? And forfaitaire means imputed. So it's not real, you impute it, right? You deduce it in some way. It's not a real return, but it's what is called in English an imputed return, all right? Okay. So you take the present value of the asset, you multiply it by some imputed return factor, and then you get a flow. So what are the units of this? What are the units of this thing? If this is a present value, this is units of, say, dollars or euros. This is a frequency, is 1 over year, right? So the whole units here is, okay. It's like a flow, right? but it's not really a flow. Nothing is flowing. You're just imputing it, okay? Huh? In all of you also have a tax system. We have these boxes. I don't know how many of you know that. Box 1, box 2, box 3. And in 1 and 2 are in the time domain. So you receive your money in income, boom, you got to pay this percentage, okay? And just whatever you received up till December 31st, they'll take their piece, okay? Box 2 is about dividend income to the company. Whatever you get paid out, all right, this is what they tax you. But box 3 is different because you have these investments and you're not selling it. You're not getting anything. So how are they going to tax that? Now, their job is to tax you, right? If you're confused about that, then just live a little longer and you'll find that out. Huh? You know, as the old saying goes, there's only 2 things that are for sure in life. All right, you know what they are? Huh? Death and taxes, okay? So you got all this property, they need to tax you. So they got to figure out a way to tax you, but how do they do that, right? Well, they just say, hey, you have these assets. You should be able to make a return of this on it, right? Huh? So you know what? We'll take 30% of whatever we decide that you should be able to make on it, right? And what is it that you should be able to make? In the old days, they took Dutch government bonds and said, well, you could have done that, right? Then, of course, when the government bonds paid 0, they didn't lower it, so everybody still kept paying, okay? Huh? So the problem with this, and there's a lot of problems with this box 3, as you know, because it, I don't know if you know that, but there are a lot of problems, and there's been lawsuits, and it's illegal, and it is illegal, right? So they found that out. But from an engineering point of view, it's kind of interesting. You're adding a time domain signal to a frequency domain signal, right? Now think about that. That's not a clever thing to do. All right. So when you are doing controls, you're either in the time domain or in the frequency domain. You can't add them, be halfway, and then add these 2 things. Okay. Huh? It's not going to work. Okay. You're going to get something weird. Either you're going to tax them too little, that you hear nobody complain, or you're going to tax them too much and you get lawsuits. All right. Huh? Okay. So you can't do it. So this whole system is from an economic engineering perspective, you can already say this thing is unfixable in my eyes, unfixable, all right? You see, it will be fixable if you paid the frequency domain taxes in frequency domain money. So, but they don't force you to pay it in time domain money. You gotta really pay this. So you somehow have to sell these assets, which you can't, then you have to borrow, and you know, huh? You see? So it's a big problem, huh? Okay. Anyway, I think it's worth mentioning that for us, keeping them separate is important. You can do all the tax system either in the frequency domain or all in the time domain, okay? All right, but not both at the same time and then add them up just because the units match, all right? Okay, this is not a real velocity. This is not a real current if this is a charge, right? Okay, all right? Anyway. Now, I have a little bit of a problem because I wrote some stuff underneath here that rolled off the slide. But I know what it was, all right? But anyway, so if you take an amount, you know, you can have an imputed flow, and if this amount is currency, then you can think of this as imputed income. This is very common. And if you do it twice, you just get an imputed growth, right? So if this is income, what will be S times the income? Well, that is how much that income changes, and you will have some imputed growth factor. You can go on like this, right? Okay. And then you can also look at P, right? So that's your willingness. And then you can multiply S times P, huh? And you can give that also a name. And what I think I called it, for some reason I'm doubting now, was this is your intentions. Huh? Well, that was just a nice idea. You can also call it your imputed present value, of your imputed willingness. Huh? I think I called it the intentions. I thought about these things a while ago. I'll fix this slide later. All right, but this should you this. What you got to see is that this thing normally is what we call the differential operator or the Heaviside operator. You know, Heaviside used this. This is what Heaviside. See, Heaviside, he was a clever guy, and the reason he was so clever is he didn't study at a university, and he had these differential equations, and he didn't know how to solve them. So he invented out of nowhere this operator, which is now called the Laplace transform or blah, blah. But he just said, okay, use this operator, big D he used, and just write for every differentiation, multiply by this D, all right? And then he was able to solve everything and do great work. And then later on, people said, hey, that can't be right, but he was able to solve every problem. Then finally, some guy figured out, I think I know who, but I forgot his name, a German scientist, that if you use a Laplace transform, you can give this a mathematically rigorous basis and blah, blah. And now what do? We teach the students this Laplace transform and immediately go to Heaviside's table and just solve problems, okay? So no, nothing was gained except that you think that you're being more rigorous, okay? So this is what he called the Heaviside. This is what we call the Heaviside operator, right? The Heaviside is really the guy who developed all of this, okay? And what for me is interesting is that the taxman and accountants, they are like more like Heaviside, you know? They don't know how to solve a differential equation. They don't learn that in accounting class, okay? But what they do is they have this idea that you just multiply by this thing to get a flow from a quantity, right? So they have this value of this house, and they somehow know how to multiply and then multiply again to get a growth, you see? And that's just basically Heaviside's idea, all right? Huh? So to me, it's always interesting that these things just pop up naturally, and then because all this work was done in formalizing it with the Laplace transform, we then go back and say, hey, we can do that here too. Okay? All right? So now it should be completely obvious how to deal with those problems that we did in the economic engineering part, right? We got all the tools. So we got our Laplace transforms of the flow and the once. And then we can calculate anything else by just multiplying or dividing by our imputation operator. So we can unimpute. Actually, that's capitalizing. Actually, when you do this, you call it capitalization. So, okay. So you take a flow and you turn it into a stock, and it's called capitalization. So you say, all right, I should really do a flow. I call this a flow. So V, I don't know, or big F, and divided by S, then you capitalize it again. There's also an imputation, okay? It's not the same as a present value. You just take a constant rate and you could capitalize the thing, all right? It's called capitalization. One of these days, I'll make a small lecture series where you do this. This was just an intention to intended to give you the flavor. All right? Huh? Okay. There's a lot of really cool stuff, you know. You can imagine you can take this transfer function and you just draw a Bode plot, you know. I don't know how you say, you know, whatever. That phase shift, right? And then suppose you have, I don't know, farmer or supply line, and you want to know, what is the optimal frequency of trading? You know, obviously you don't want to be sitting here. You know, nothing is going to get through. You know, you're sitting there buying winter coats, you know, in the spring, or in the, you know, you're sitting there buying fur coats in the summer or something. You know, half the time there's no good, right? You got to be where this system is trading through, right? So you can use Bode plots, you can do all kinds of stuff. Some theses have done that. Okay? You can just go nuts on your controls tools. All right. let's go. And this is the system that we had. This was this dealer. Huh? So, what was it? I think it was, oh, it was this thing, yeah. Okay. So this was this inventory manager, right? So you're looking at if there's some exogenous desire, or how is your stock going to respond, and we will see how you can manage that inventory, okay? Huh? By changing the damping, right? So there's a various question of this friction. So there's a propensity to discount. Right, so what we want to do now is look at this from the frequency domain. So you guys all know this, right? Huh? You put a bunch of S's every time you see a dot, huh? And then divide it and multiply and blah, blah. And I always get it wrong, but I think I may have gotten it right this time. This is what you get. This is the same picture, but now in the frequency domain, right? So here you see clearly how you're imputing, right? So you have the thing itself, and you impute once, and then you also look at a growth, right? Yeah, of course, because you have this Q double dot, right? So you know that not only is inventory growing, you know also how it's accelerating, right? How the demand is, you know, how the demand is extending, okay? I think I got them right, but it doesn't matter, right? This is the important part. Now, from this, you can calculate what the poles are. So if you have this underdamped system, you would have these two poles, right? Huh? Okay. So this complex discount rate can be plotted here in the complex plane. This all, and here they would be. Right, so you could just read off, well, you guys know all this, right? This is then the frequency omega d. And this is the damping. This is the sigma, right? Huh? This is the omega part. I find it interesting because, first of all, this was the trade cycle, but you see the effective trade cycle when there is market friction goes down, and it becomes the sign of this, this thing, okay? And the propensity itself is the cosine of the angle. So this angle here is the R cosine of zeta, I believe, right? Huh? You see that? Because I take omega n, so that's my natural trade cycle. And then by multiplying by the cosine, I'll get to this point here. So this zeta, right, the damping constant, which is the propensity to discount, has to be the cosine of this angle that the the pole makes with the origin. Okay, you guys know this, don't you? Huh? This is bread and butter. Huh? You probably look confused because you're just bored, huh? Okay, so it gives a nice picture of what's going on, right? Actually, this picture is really nice because what happens when zeta, the propensity discount is 0? Well, then you're over here, right? Huh? Okay? And you got this, you're just a trader without any transaction costs. You're just going, woo, 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 huh? All right? And you can keep increasing it, you know, so you'll have some discount going on, and you come a little slower in your frequency because the transaction cost is slowing your trade cycle down a little bit, right? Huh? Okay, so if this is the cosine, then obviously this is the sine, because the sine is 1 minus cosine squared, right? Huh? There's the sine, and then you take the square root and you get the sine. Huh? Okay. And then you keep going and going till you hit this pole hits there, and this one hits there. Okay. And then the frequency is going to be 0, right? And you'll have this solution here. This one here, right? Okay, so you just have this damping factor, and you retain a linear factor here because you still have two poles that are epsilon apart. So this sine here becomes proportional to omega over 2 times t, right? Huh? So this thing goes to 1. And then you are left with this little thing here. That's when the poles are on top of each other. Then here something interesting happens. So when you increase your damping further, you get these poles spreading out, right? With the cosine hyperbolic and sine hyperbolic, all right? Now, how does that work, right? So when you go further, you'll see this pole coming in and that pole coming out. Now, you can say, why is that? You know, normally these get treated like, you know, some real pole, like this is S1 T, and this will be S2, e to the S2. But it's nicer to see it as a caution, a cinch, you know, because you can actually see it like this, right? So this will be the complex plane, and then you put a hyperbolic plane here. So you could draw this pole, and then this one goes over there, and then, you know, now you can make a little Riemann sphere, and you can draw this whole thing. I'm not going to do it, huh? But you can see that there's a lot of structure in this graph where you just pull it out. And I guess what I want to say is the thing you guys all know. You can steer yourself like crazy on these graphs. And here, by just looking at these poles, you know everything, all right? And you know what's going to happen if you increase the damping, and you know when they go apart, and you get a fast one. Here's the fast discount, and here's a slow discount. So you get the hyperbolic discounting, right? Huh? So this will be a very fast pole, I think, right? So that's what he wants to consume immediately. And this will be the slow pole when they go apart, which is going to slowly eats the rest of what he has, right? So the hyperbolic discounting is here. This will be the ideal exponential type of discounting, and this will be more of a trader. So it's very, very efficient, okay? Instead of all these graphs, very efficient. Just a little piece of geometry. Here I drew the different signals. Took some time to do that. You guys know all the rest, huh? This one is wrong, right? It should be like this, huh? Yeah. Yeah, that one is wrong. The minus sign in the code, huh? No, that's right. I think I know what I did. I already know what the mistake was. Huh? Well, thank you. Now, this one is not wrong, right?
No, this one.
This one is right. This one is right. So listen, if you look at the economy, you look at the business cycles in the economy, you'll get an article anywhere, say Wikipedia, and it says there are, I don't know how many cycles, 6 cycles or something. They have an inventory cycle, they have a cumulative cycle, they have a long inventory cycle. I don't know what they're called, you know. Somebody can look it up. Economic cycles, can you look it up? Huh? Just quickly, huh? There should be a Kondratiev capital cycle, and you're not finding anything? Yeah. Business cycles, the economic cycle, well, whatever. Huh? Cycles, economic cycles, huh? Kondratiev, yeah, there's a whole bunch of them. There's a Kondratiev wave, the kitchen wave, huh? Yeah, they have a whole pile of them, huh? Yeah, yeah, here's one. So they have I think they have, there's one article on Wikipedia where they have all the cycles. Let me see, huh? Economic cycle, Kuznets cycle, huh? A whole bunch of them. I think there's 6. Kitchen, Juglar, huh? Here. Yeah, the pork cycle. Huh? So there's the inventory cycle, a Juglar cycle. So that's 3 to 5 years, 7 to 11, 15 to 25, huh? Okay. So what do you know? Well, omega d here is what? Is 1 divided by that, right? Huh? So you just read them off, okay? Huh? Then, okay, so you can already read off the imaginary part of each of the poles. So if they have 1, 2, 3, 4, how many cycles do they have? 12. Okay. Now let's look at this one, 4. What's the order of that model, your system? 4 cycles. Huh? What other is it? 8 or something? I always forget. Huh? Second order model has 1 cycle, right? 2 poles, but they're conjugate, right? Huh? So 4 cycles, you need an 8th order model, right? Huh? Yeah, that's it. There you go. All right. Now you have to know what the poles are. So, okay, huh? So here they tell you what the imaginary part of the poles are. All right. Now you need the real part of the poles because you need to know how each of those is damping, right? Now, that's not here because they don't think of it that way, but they have other concepts. It's called the own rate of interest or the own discount rate. It was advanced by Hicks and Keynes that each commodity had its own particular rate at which it was discounting, okay? So capital has one, pears have another, and this. So if you look at pork, now it probably has some kind of own rate of interest, and you just attach that to that, right? And there you go. That's your first jab at a model, right? Now just to program it in. Get your PC Spice, or what is it, the LT Spice out, just throw in that model, and you got an economy already, right? You don't know why the heck it's got that. So it's better to build it up, but you just, for every cycle, you need at least a mass spring and a damper, right? Huh? So you start building that up, so you'll need some demand. So here you have your kitchen cycle. So you'll need some demand, well, inventory, there's demand for inventory, right? Then you need some storage, well, obviously, otherwise it wouldn't be called inventory, right? Huh? And then you need a little bit of transaction costs, you can figure that out. Oh, then you will start building a model like that, right? Okay. Now, how do you calibrate it? Well, you just calibrate it the same way the old-time engineers did. You made the circuit board, and you put on an oscillator, and you find that it peaks. Yeah? So you look at your Bode plot, and you go, hey, here's my peak. Okay, huh? So why don't I just choose my K and my M and my B so that it all fits, and then you're done. All right? You see? No more data fitting in the terms of time series, okay? Huh? Otherwise, you're sitting there time series. And when you do that time domain, you say, how am I ever going to measure the mass and the storage constant? Well, just do this frequency domain. It's like, huh? This is how the old timers did it. You just took a circuit board, put a generator on it, and see when the thing oscillates, Just go, huh? Okay? If you have a supply line, they have this thing called a bullwhip effect. So they saw that during COVID. You get these demand shocks, and at a certain point, this supply line starts going up and down, and it can't deliver. That's the resonance frequency. Let's find out what it is. You can see, if you think of your supply line as a second-order system, it's probably a lot of them in series. Chap, here's a model. All right? Huh? Okay. Fixed investment. Now, obviously, there's demand for capital, right? Real capital. And also there's storage of it. Otherwise, those factories wouldn't have that stuff standing there. Of course, there are transaction costs associated with it. So here's another cycle. So every time you have a cycle, you're going to have some demand, you're going to have some storage, and you'll probably have some costs, because it will be damping. Because if it wasn't damping, nobody would be making any money. All right? And if there's one thing guys don't like that, making no money. All right? Huh? So I think Well, this is a separate topic that we can expand on, and you can talk about controllers too, and then you'll see you have a PID controller, the I thing, you're basically integrating, so you're using the same imputation operator on a signal, right? And you're capitalizing, and now you can think it all through using these frequency domain concepts, okay? You can go, I already mentioned Bode plots, you can use Nyquist plots, you can do anything at all, really, that you can use, because you now have the tools to interpret those things, okay? You know what it means for a complex present value, because you know what that imaginary part is doing. It's keeping track of the business cycle. It's important. Anybody who's traded knows that it's not just a question of buy and hold, where you just know things are growing exponentially. No. Things are, you have to buy low and sell high, and yeah. So you got to know what the frequency is if you're trading, okay? So all of these things are, and the way of thinking in the frequency domain is much easier than in the time domain, because you can think of this demand graph as just a graph that's just there, instead of having three graphs, one for a mass, so one for demand, one for a spring, that's another graph, and then one for a damper. So three graphs. Now, if you do it in the frequency domain, you just throw everything in one complex impedance, okay? You don't sit there with all these different elasticities. You do one complex elasticity or transfer function, and you're done with it, okay? You can characterize your system with Bode plots. So you just need to keep track of the amplification, the gain, and then the phase shift. So the phase shift, that's like a deferral, right? So something is happening, and then 3 seconds later, that same tendency will go over there. That's your phase shift, So you see this all the time, the goods are being delivered, and the prices, they catch up a little later. Why? Because the supply line has got these mass spring damper systems, and they imply this phase shift, Okay. So it's very natural and easy to think in these frequency domain terms, very, very natural. And my feeling is, if you read Keynes and in Hicks, those are kind of the more non-mathematical economists. That's what they did, really. They were really thinking in the frequency domain, And that's what the taxman does too, when he does his imputed income, and and when people have present values and other things, they think in the frequency domain. You have other concepts like bond duration. So if you have a bond, you look at its present value, all right? So you know what a bond is? It's just some contract that pays you some kind of, for 10 years, some coupon, you get, and at the end you get your money back, okay? So you can calculate, this is a cash flow, say VT, right? And you can just calculate what the present value of that thing is by just calculating this. This is the amount of money that is, in this sense, equivalent, okay? All right? Yeah, so I just wanted to finish up with a little thing about other ways you can use the frequency domain. So bond traders do this all the time, okay? So does any one of you know anything about bond trading? So, no? You know what a bond is, So a bond is something that it gives you, basically you purchase a cash flow, right? Because you get these coupon payments, okay? And if you have a 10-year, then they stop in 10 years, okay? And then you also get all your money back. That's not so interesting. That's just an impulse, okay? So let's just focus on the coupon alone. That's sometimes called a strip, all right? So how much is that worth, all right? Now, one way of saying it is to look at the present value. So you just look at, exactly this thing, the Laplace transform of this bond, okay? So you can calculate what it is. It's like 1 over S, and then you have to subtract something. You have to subtract, the other thing. You know how to do that, right? So you don't get 1 over S anymore. You have to do some shifted signal and subtract it. And the shift is like e to the minus S tau, where tau is exactly this, the expiration of the bond or the maturity. And then you subtract that. All right? okay? Huh? I think it's 1 minus e to the s tau times 1 over s, something you get like that, okay? Yeah, because 1 times 1 over s, that's a perpetuity. This is a shift. So tau is the maturity of the bond. Huh? And then you take the same thing, but you shift it over tau, and I subtract it, okay? You can look it up. You'll realize I made another error. But that's the idea. You can, huh? No, but the point is you can just calculate easy, right? So that's the present value of that bond, okay? And as higher the interest rates, the higher this present value, obviously, right? Huh? Okay, right? Huh? So now the question is what's going to happen if interest rates change? So here's a problem. So you have this bond and it's paying you 5% interest and you're happy. While you're thinking, okay, the money is streaming in. And then all of a sudden interest rates go up and everybody else can get money, bonds that are paying 7%. So all of a sudden you're not so happy, right? Huh? So suppose you paid 1,000 euros for this bond, and now interest rates are at 7, and you want to sell this bond. Now nobody's going to give you 1,000 euros for it, because if they spend 1,000 euros, they're going to get a bond paying 7%, right? Huh? So no siree, bye-bye. Huh? But there will be a price at which they will buy it, and that will be exactly the price. That's the discount that makes up for the interest that is not received, right? Okay, the foregone interest, okay? So the price of the bond, the present value of that bond will have to go down, all right? Okay? This is what's called interest rate risk, or one version of interest rate risk, okay? And what happens is the longer the bond is, that means the further the maturity, the bigger this effect. You see, if you get interest rates change and your bond is about to expire tomorrow, what's the difference? It's not going to make a difference. But if your bond still has 20 years, the long bond has got 30 years. If it's 30 years, you're going to have 30 years of misery ahead of you, right? So that thing is going to, So the longer the bond, the higher the duration of the bond, the bigger this effect, okay? Now, what is the effect? If this is the present value of the bond, right? This is our present value. Then we want to know how this value changes when rates change, okay? Well, how would we measure that? Well, here's an idea. You look at the change of the value and you divide it by the change in the rate, okay? What do you call this? You call this the frequency domain derivative, right? Okay. This is the frequency domain derivative, okay? Put a minus sign in front of it, and this is called the duration of the bond. Because it has, usually they'll multiply it by 1 over q, So this will have dimensions of time then, because S has dimensions of 1 over time. So it's like a duration. So they look at the percentage change, right? So dqs, that's what we would do too. If you would look at a Bode plot, you look at the log. So it's really the log of the, This is what they really do, but it's the same thing, okay? It's called the duration. So that, in a sense, measures the risk, the interest rate risk. So the bigger this thing, if it goes the right way, you're doing good, but if it goes the wrong way, you're suffering. So the bonds where this derivative is the highest, they are the riskier ones, okay? Okay. So the frequency domain derivative is precisely bond duration. And you can look at the second derivative. That's what they call bond convexity. So not only is the duration changing, so if they look at these Bloomberg terminals, they'll see the duration, and then some sophisticated guys will know, well, if the duration changes a lot, then I actually have to also look at the convexity, like how much is that change accelerating away from me? It's called bond convexity. So bond traders look at these numbers, okay? So bond traders are fully in the frequency domain, and they're looking at the Taylor series expansion of the Laplace transform, and they're going through that, okay? Now, let me ask you the following question. If you have a frequency domain derivative, right? Huh? What is that in the time domain? Huh? Look, I ask you another question. If you have a time domain derivative, huh? Which is q dot, what is that in the frequency domain? You know that? Sure you do. Well, tell me. Huh? Yeah, it's q, of course, right? So why wouldn't you know this one? Well, yeah, it's just t. Go and look it up. All right? Huh? Huh? T times v, sorry. Huh? Huh? Yeah, because the Laplace transform of this is that, right? Huh? Okay. Okay. This is called Macaulay duration. Macaulay. And this is called modified duration. And bond traders never know which to use. And I don't think it's clear to them that they tend to match it up. The most academics use this, most practical guys use that. And it's just like box 1 and 3. They kind of don't see the difference. You can use either, but you got to do the Laplace transform. You got to go to the other one, right? And you could define something called Macaulay convexity, which would be this, right? But I don't think I've ever seen somebody do that, okay? So bond trading can also be done in the Laplace transform in a very nice and rigorous fashion, all right? Huh? You see? This is just a nice application. There's a bunch of other examples. I think the time is up, and I think you guys are done with examples on this. So later in the year, I may do a special little. This should really be written up in a small paper. I never got around to it, but I will do a little bit more of it. But I just wanted you to know, so that you see it's there, and there is a lecture. You can go to YouTube, and if you use this for your thesis work, you know, just look at it and come to me, and we can discuss further aspects of this. Okay? So with that, I'll end this. Now, next week, when is our Rabo symposium? It's on the in 2 weeks, yeah. So what I want to do on Thursday is I want to give 2 practice presentations, one of yours and one of yours, Jeroen. Huh? All right? And I'll give an introduction, all right? And then you show your model, and you show your model, and then we'll all attack it, all right? Just go nuts on these guys. Because that's the thing that helps them, you know? And I think we've got really nice research. You'll find it interesting as well, because Berend has a really nice model where you integrated the bank with an economy, all programmed in SPICE. Jeroen has a more theoretical thing, but it's now, Jeroen, it is implementable now in SPICE, right? It's running, and
yeah. I can show some simulations.
Yeah.
Nice. So it's not only theory now anymore.
Yeah, so that's where we did Black-Scholes kind of pricing on using economic engineering. All right, so that will be a good, really nice session. And then afterwards, I want to do rotations and capital, and there was something else I wanted to do, and then finish off this series, and then go on to the next paper of the electronics, how you do the electrical circuit design, and then we'll do the end port system design. Okay. All right. Okay. We'll wrap up the show. So